o'clock. And with that, I just have one quick assignment for all of us. Go quickly around the table. We've got a bunch here. So just go around the table and identify yourselves and maybe where you retired from if you want to add that. I'm Dick Strombotny. I retired from the U.S. Department of Transportation.
Wayne Warren, retired from Goddard, teaching at University of Maryland, University College.
Don Novotny, retired from NIST.
Don Feldman, retired from UMD.
Rudy Coutard, retired from the Naval Research Laboratory.
Joe Zika, retired from Northrop Grumman.
Saul Glass, Howard University.
Al Feldman, retired from NIST. I brought my two grandchildren to work, one in Maryland and one in Muhlenberg.
Welcome.
Sheldon Fisher, retired NRL, and part-time at George Mason.
Oh, Nicholas, chemical engineering major at Montgomery College.
Joe Rosen, retired from Tel Aviv University.
George Hutland, retired from the Army Research Lab, now doing time at Prince George's College.
Jim Moore, retired from NRL.
Dragner's NRL, retired.
Ed Conrad, Nuclear Defense Agency, retired.
David Abraham, visiting from Andromeda.
Walter Faust, retired from NRL, much longer story. My mother-in-law forced me to leave a full professorship at USC in Illinois, and I hate her still 42 years later.
Well, I'm glad you don't bear a grudge.
That's ancient history.
Don
Yeah.
Michaels at NRL Space Science Majors.
Harold Williams, not retired, Montgomery College, planetarium. I teach astronomy, do other things too.
Michael Bansky at David Taylor Model Basin.
Rupert Chappelle, Montgomery College, I collect photons and distribute them.
And you too.
And Jack Gaffey will introduce our speaker.
Jack Gaffey, retired from the University of Maryland and NASA Goddard.
I'd just like to add one more thing about my background.
Okay.
For these people here, I got my degree at the University of California, Berkeley in physics for $37.50 a semester. That's the way it should be.
For a good price.
I paid $53 when I went to UC.
When I was there, it was $50 a semester. It was $300 a semester as a graduate student until Reagan became governor. It's a great pleasure to introduce our speaker today. Is Ted Jacobson. He got his PhD at the University of Texas in Austin. He was a postdoc at UC Santa Barbara and Brandeis, then came to the University of Maryland, where he's currently works on gravitational theory. He's a fellow of the APS, the AAS, and holds a distinguished visiting research chair at the Perimeter Institute of Theoretical Physics in Waterloo, Canada.
Bravo.
Today he will tell us about black hole entropy, entanglement, and holographic spacetime.
Thank you, Jack. Hello, everyone. I'm really impressed by the crowd, the size of the crowd. I expected
This is larger than usual. I tell people it's typically 15 to 20, and this must be 25.
because I came thinking I would say, oh, well, it's just such a small group, just stop me whenever you want and ask questions. And actually, I think I'll still say that, because, you know, I'm sure the diversity of the backgrounds
32.
makes it, you know, unlikely that I would give a talk that would be 100% impedance matched to anybody. So
Yeah, we are a very diverse group.
just feel free, honestly, to stop me at any time, and I'm happy to just cover a kind of random subset of what I might have covered. I did construct it, at least for most of it, to try to explain it to a completely general physicist. So we'll start with that. And some of you, but I guess since the crowd's so big, not very big fraction, heard this talk at Goddard. So I guess I should assume that most didn't hear it.
And some of us need to hear things more than once
Okay.
before we understand them.
Oh, I know about that too.
Better than here.
Okay, so the story is about black hole entropy and where it's leading us to. And it's in the middle, the formula for black hole entropy, which I'll be telling you about in the middle of the talk. But just to give it right up front, a black hole has a horizon that's sort of a dividing surface in space-time beyond which you can't exit once you enter. And for a spherical black hole, it's just a spherical surface. It has an area, And the entropy associated with the black hole is the area of that surface, but in units of some length squared, because entropy, if you're, is dimensionless, if we set Boltzmann's constant to 1, which we do, or I do. So that you measure the area in units of the Planck length squared, or actually to be exact, 4 times that. The Planck length is the unique length you can form from Planck's constant h bar, Newton's constant g, and the speed of light c. And Planck himself actually wrote that length down, and in fact was quite fascinated once he introduced h bar by the fact that with h bar, g, and c, he could form any unit he needed out of these fundamental constants. Yeah. Oh, that might help. Thank you. So we'll be getting to why that's, well, there it goes, where that came from and where it's leading us to. This is just a preview of some of the things that it's leading us to, or has already led us to, actually. So to understand this, really, we have to get into renormalization of quantum field theory. We get into the relationship between the Einstein equation and the vacuum as a thermodynamic system, which sounds paradoxical because vacuum is supposed to be nothing, so how can it be thermodynamic? The information paradox about black holes, which is that it looks like if you throw things into a black hole, nothing can come out. You lose any information that went in, and yet we have strong reason to believe that actually you don't lose information that goes in. Although I probably won't have time to get into this. Holographic principle, well, that should be pretty much meaningless right now, but I'll explain it hopefully at the end. Might not get to that. And this key idea that somehow entanglement entropy, which is a key concept in quantum mechanics, and I'll explain that, is intimately related to geometry, and it's sort of through this formula, because area is a geometrical quantity, and this entropy is somehow related to entanglement of quantum mechanics. In fact, entanglement of the vacuum in quantum mechanics.
Who first derived the area equation?
The first person to introduce it, I'll talk about it, was Jacob Bekenstein.
Okay.
So let's start with Einstein. Just about before he finished formulating the final form of general relativity, it took him several years to get to it, all the way from 1905 with special relativity, 10 years later in 1915. And I'm just doing this to have a little background on general relativity for those of you that are not so familiar with that. I want to basically introduce the geometry idea that lies behind general relativity. So I like to start with an analogy of just geometry of a curved surface, like the surface of the Earth. And it's clear there by just thinking about, let's say, 2 lines of longitude that leave the equator, both heading due north. So they leave the equator parallel to each other. But if they are straight lines, they're going to both go through the North Pole, which means that the distance between the lines is shrinking, and so parallel lines don't remain parallel. And that's a sign that there's curvature there. And this is in case this is positive curvature, uniform on a sphere. Now, in relativity, you can see things quite similarly, but you have to think about not the geometry of space, but the geometry of space-time. So we add one more dimension, which on this picture is time going vertically on the picture. Now, since I added one, now I have 4 dimensions, and I can't draw a picture of 4 dimensions, so I drop one of the space dimensions. And so this is a picture of the Earth at one time. It looks like a disk instead of a sphere because I had to drop a space dimension. And then as time goes on, that disk sweeps through time, and it makes a cylinder, and that's called the world tube of the Earth in space-time. Now here's another thing. Here's an apple at one time, sitting above the surface of the Earth at some height. And if we let go of the apple, and it starts at rest just like this in my hand, I could have brought an apple with me, but I didn't. It would start out parallel in space-time, because both the Earth and the apple are going in the same direction, namely forward in time, and they're not moving relative to each other. And yet, you of course know if I let go of the apple, it falls. And in the picture of space and time, that's, you see that as the line of the apple approaches the line of the Earth. So these initially parallel lines in space-time don't remain parallel. And in general relativity, that's interpreted as being due to the curvature of space-time. And it's a direct consequence, just very closely analogous to that one. An interesting thing, let me just go back to the Earth. So you know that like if you're flying between two distant points on the Earth, you tend to take a path that goes, it doesn't look on a Mercator projection like the straight line you might have picked. You go up towards the pole because there's less distance around there. If you're going from one longitude to another, you can travel it with less distance if you go up towards the pole because the lines of longitude get closer. Well, it's the same way in space-time, except it's kind of opposite. Time is running faster up here than it is down here. And so, in fact, here a straight line is the shortest distance between 2 points, but in space-time, a straight path of an object is the longest time between 2 points. And so here's a picture of how that works out. If you toss the apple up, it goes up to some maximum height, falls back down, and I claim that's actually a straight line in the sense of the longest distance between these 2 points, but by distance I really mean time. So you could say the apple goes up because time is running faster up there. Now you want to know how much faster. Why didn't I notice that? And it's because it's a fairly small effect. It's 1/1000th of a second, that's 1 nanosecond, for every foot that you go up per year. So that's the amount that the clocks are slow. Now, since there are about 10 to the 7 seconds in a year, that means in 1 second, it's 10 to the minus 16 seconds. And so that's 1 part in 10 to the 16. And quite amazingly, today's atomic clocks, the most precise ones, can just about measure with that precision. So they can actually detect the difference in the rate time is flowing here and here, 1 foot apart, at the surface of the Earth. It's a very real effect. One of the things that general relativity led to, and really the one that convinced Einstein he had the right theory, was that the precession of the perihelion of Mercury wasn't matching up with Newtonian gravity quite right. Most of the effect is due to the perturbations of Jupiter and maybe other planets, I'm not sure, but primarily Jupiter. But there's a residual that couldn't be explained, and actually it was quite amazing that they were even able to measure this residual, by the way, because it's only 43 seconds of arc per century. But the way they did it was by looking, occasionally Mercury's orbit passes in front of the sun, and it's possible because the sun has a very defined shape and location to time quite accurately exactly when Mercury appears on the at the edge of the sun's disk. And thereby, if the clocks are running from the previous time and you haven't lost track of time, you can tell, is it coming early or is it coming late? And it turns out the amount of this precession, the amount of this 43 seconds of arc, corresponds to about 9 minutes of advance time for the transit per century. So for every year, that would be 9% of a minute. So that's like, you know, a few seconds. Is that right? Wait, did I say that correctly?
Yeah, 6 seconds, 5 seconds.
Yeah, so then after, I don't know, we don't see these transits every year. It takes quite a while for a good transit to appear. So let's say after 20 years, 25 years, astronomers can measure another one. They've kept track of time well enough to tell the accumulated 20 times 6 seconds or something, so a minute or so difference. Quite amazing, and that's old physics and old observations. I mean, this was known at the time of Einstein's theory in 1915, how much it was off by. He calculated it. To calculate it, he had to have the solution to his field equation that describes the gravitational field of the sun. And it's given by this formula in an approximation. The formula is for this ds squared represents the proper time associated with a given displacement in space and time. This t is a time coordinate, so dt is the change of time coordinate squared, change of a radial coordinate, and the usual angular coordinates on the sphere. And this just looks like the usual sphere metric, sphere line element. But then you have in front of the dr and dt squared terms a correction. So if this rs were 0, this would just describe flat space-time, ordinary Minkowski space. Rs is proportional to the mass of the object, in this case the sun, and Newton's constant, and divided by the speed of light. So it's a length, because it's divided by length there. And it's 3 kilometers about. So that's the length scale associated with the gravitational field of the sun, yeah.
And that's really c squared dt squared, that's c equal 1 in the.
Oh, that's a good point, yeah, I should have included that.
Yes.
Well, or I should divide these by c squared.
Well.
Because I like to think of ds squared as telling us how much time passes instead of how much space. But okay, so then he got this, you know, his field equations were in a way elegant and beautiful and everything, and especially now we understand how to deal with them, but they're very complicated. Partial differential equations for 10 different functions and 4 different variables, nonlinear, and he didn't think he'd ever solve it, even for the case of a spherically symmetric static object, but he didn't need to solve it exactly to get this. This is an approximation to first order in this mass quantity, and in the ratio really to c squared. You can see that higher order terms would be suppressed by more powers of the speed of light in the denominator, and so they could be neglected for his purpose. But actually it turned out just the same year, even a couple of months later, somebody did get the exact solution, and this is where the story of black holes begins. So Schwarzschild, who was an astronomer and mathematician, and actually had already worked on related things, came out almost immediately with this exact solution. If you can see it well enough, you'll see that it almost looks exactly the same. This term is exactly the same, and this term is exactly the same. The only difference is that here we have the inverse of 1 minus rs over r, and if you Taylor expand that, the first order term in it is what I showed you before.
It's 1 plus r, yeah.
So this is, but this is now exact, and it has a strange feature. Because it's exact, we have to take it seriously, and he thought of it as the gravitational field of like point particle, but it has a strange feature, which is that if r, the radial coordinate, becomes equal to r sub s, which remember that's 3 kilometers, and if this equation still applies, then this becomes 1 minus 1, 1 over 1 minus 1, so it's infinite. And this term becomes 0, so something is going haywire in this formula at that place. And Schwarzschild, well, for the sun it doesn't really matter, because the sun is bigger than 3 kilometers in radius. It's like 100,000 kilometers or something. So by the time you get into the sun, this equation stops describing the gravitational field. But you could imagine a compact object, maybe, it certainly could have then, such that you could get that close, and then it would go haywire. So Schwarzschild had this to say about that issue. He said in order that this, he called it a discontinuity, it's really a divergence or an infinity. In order for it to coincide with the origin, like the center of space, one should define the radial coordinate appropriately. Well, I can't go into it, but this is a totally confused statement. It's completely incorrect. Once, you know, if you put r, I can go into it and say one thing. If you put r equal to r sub s, which is where this craziness happens, then look at this piece here. That's just the radius. That means you're looking at a sphere whose radius is 3 kilometers in terms of area. There's nothing crazy about that. And it's certainly not the center. It's not the origin, because it's a finite-sized sphere. So that was wrong. The same year, actually, a student of Hendrik Lorentz in the Netherlands was doing his PhD on this subject, and he understood it a little bit better. He didn't propose that, but he said a moving particle can never actually get beyond that radius because it would take an infinite amount of time. Well, he was right in one sense. It would take an infinite amount of this t coordinate. But one of the tricky things about general relativity and essential things is that coordinates don't have any physical meaning directly. You have to formulate physics in terms of observable quantities, like the proper time that an actual clock measures. And this formula tells you the relation between that time and this t coordinate. And well, it's that relationship that's going haywire. It's not the time on an actual clock. So Droste also was wrong. Somebody about 16 years later did understand it. What? Yeah, 16 years later. That was one of my heroes, this guy who's actually a priest.
Lemaitre.
Lemaitre, he is a Belgian priest, also an astronomer, a mathematician. He understood precisely what was going on at r equals r sub s. And he said, the singularity of the Schwarzschild field is thus a fictitious singularity, analogous to that which appears in the horizon of the center in the original form of the de Sitter universe. Well, I don't have time to go into the de Sitter universe, but it's another solution to Einstein's equation, which had a kind of horizon beyond which a given observer couldn't see anything because the universe is expanding too fast. And he recognized that the black hole horizon was really strictly analogous to it. But nobody picked up on what he said, partly because, I think, because he wrote his article in French in an obscure Belgian journal, and also because he's a modest person. You can tell by the way he's standing. He didn't, shout out to tell everybody what he'd figured out. By the way, he's not just a priest. I mean, he did his education at Cambridge University and MIT. His PhD was in astronomy, and he pioneered the physical cosmology theory and the theory of the expanding universe, the cosmic fireball, the origin of structure in the universe, and even hypothesized a beginning of time that's quite analogous to the way we describe the Big Bang today. By the way, it's not the beginning of time, it's the beginning of where we know how to talk about time. Okay, so here's, if it was puzzling to you, and it was to many people, an analogy of a black hole. So what's happening at R sub s? Now we know that Schwarzschild solution must be taken seriously, and it's possible if a star were to collapse smaller than 3 kilometers and have the same mass as the sun, then this R equal R sub s surface would be occurring, and what's going on there? Like I said, it's a horizon, but to understand what that means, I want to show you this analogy. So this is a spillway at a dam in California. Water flows down the hole, and the analogy I want to make is this red dashed or dotted line will be an event horizon, like a black hole horizon. So imagine you threw a pebble into this water, and waves went out from it in all directions, traveling at the speed of surface waves. Then they would go out roughly in a circular shape. But if you toss the pebble in closer to the hole, then because the water is flowing down, the waves that are going downstream will travel further than the waves traveling back upstream. In fact, so it's an off-center kind of a circle there. And if you tossed the pebble in just at the right critical place, where the dashed line is, it would look like this. In fact, no waves would go upstream at all because the flow speed of the water here down is exactly equal and opposite to the surface wave speed going up. And so at that point, all influences carried by surface waves would be swept in beyond this line. So this is just the way it works in space-time. Instead of ripples on water, you have light waves or electromagnetic waves of other kinds, or even gravitational waves or anything, because we know in relativistic physics nothing can travel faster than the speed of light. So it's as if space-time itself, or space itself, is flowing into the black hole faster at the speed of light at the horizon. A very strange thing. Now, like I said, people didn't pick up on Lemaitre's insight. That was in 1932. Some years later, I think it's just about 7 years later, Oppenheimer, with a student Snyder, studied the collapse of a fluid, like a star, to form, but they didn't assign it pressure, so it couldn't hold itself up. So it would collapse smaller than the Schwarzschild radius, and they wanted to see what would happen. And they did this analytically, partially, and in approximations. And they figured out what happened, and they wrote a paper about it, and it was called On Continued Gravitational Contraction. And the key conclusion in the abstract here is that the total time of collapse for an observer co-moving with the stellar matter is finite. So you can fall into this, and your time on your watch reads a finite time as you cross the event horizon. But they point out an external observer sees the star asymptotically shrinking to its gravitational radius. In other words, somebody staying outside can't see anything beyond this horizon. And so they would just see sort of the collapse slow down fact, exponentially fading away in brightness, and that's it. That's all they would see. So this was an extremely clearly reasoned and vivid paper. 1939, that happened to be a time in the world when other things were going on that distracted people, and so also people didn't pick up on this. Here's a citation chart of that paper. Well, it starts in 1946, so that's already 7 years after the paper was written. 0 citations. After the war, in around 1948 or 9 or 50, there were a couple of citations, not about they had to do with nuclear physics and the theory of stellar structure. They weren't about this horizon. And it wasn't until, and even this one wasn't, it wasn't until I think the second one there, Charlie Misner, I think, cited it, probably knew about it for many years because Wheeler and his school at Princeton were thinking about black holes already, but nobody had written about this paper. Now it's just, exponentially taking off. This is 2018. So now this is widely regarded as, the paper where this was first understood, even though it took decades for people to react to it.
Did Einstein understand what this was about?
No, he didn't. In fact, he wrote a completely specious paper about it the same year that they wrote this paper, arguing that it was inconsistent with the theory to ever have an object that was collapsed enough to have a Schwarzschild radius.
What's the difference between the yellow and the brown bars?
I actually don't know.
One is citations, the other is a publication year.
Right.
Oh, the number of citations.
It might be
Citations
published.
slash
It might be
publication.
published versus total citations. Because some citations are like in preprints or something.
Yeah.
I don't know.
Because the yellow are much smaller.
Oh, is it on top of that or is it behind? I see. That's it. Okay, I don't know what it is.
Oh.
It doesn't matter. This is the next thing is to illustrate that even by the end of the 50s, which is like 20 years after Oppenheimer and Snyder's paper, and even though Wheeler was very interested in general relativity, he still didn't accept Oppenheimer's result. There was a meeting in 1958, the Solvay Congress, where Wheeler argued the collapse theory, that is Oppenheimer's theory I just described, does not give an acceptable answer to the fate of matter in such a star. I was very curious, what's not acceptable about it? Well, if you look very closely at other things he wrote at the time, he was thinking there had to be some reason why this didn't happen. It just seemed unthinkable to him that you would have collapsed to nothing. And he thought, for example, that matter might convert to radiation once it became very dense, and then the radiation would just escape before it finished collapsing. Turned out later, Roger Penrose proved that, according to general relativity, a mechanism like that couldn't possibly save the star from forming a black hole anyway, because there's a kind of point of no return. Once it was sufficiently condensed, but before it should turn to radiation because nothing horrible had happened to it yet, it's already too late for anything to turn around. The equations of general relativity would say, Penrose invented the concept of a trapped surface. So he could prove that the equations said, it's too late, you're gonna have a horizon. Well, Oppenheimer's response to Wheeler was just, wouldn't the simplest assumption about the fate of a star, more than the critical mass, that means so it would collapse, that it undergoes continued gravitational contraction and cuts itself off from the rest of the universe.
Wow.
Well, it is simple, but it's difficult to think about. Yeah.
Yeah, well, it seems to me that the matter outside the event horizon contributes to the mass of the black hole. Any matter closer than an observation point contributes to the mass. The masses of a collection of objects is located at the centroid, the center of the object. And that whether that center is inside a black hole or not makes no difference as to what counts towards the mass of the black hole.
Outside, you mean?
A lot of the stuff
Yeah.
outside the black hole contributes to the mass of the black hole.
But it would fall, I'm not sure I'd say it that way. I think nothing would, things outside will generally, if it's not orbiting, fall in, right? Or if it's, let's say it's a supernova
Yeah,
explosion.
but whether it's orbiting or not, if it's in the vicinity of the black hole, closer than you are, then it contributes to the mass of the black hole.
Well, I would say it contributes to the mass of the whole space-time, but certainly not to the black hole, because if I
Well,
go closer.
If you have any set of objects considered as a group, their mass is located at the center.
I see what you're saying.
of
I
all
think
of
you're
them.
just saying that if I'm outside the whole group, I will be attracted to the whole bunch of it by both the matter outside the black hole and the matter that fell in.
Yes.
The total mass will attract to me.
And so the
Sure.
mass of what's inside
But if I go
includes a lot
closer
of
to the
mass of
black
what's
hole,
outside.
if I go inside, let's say you have a shell of matter around the black hole. If I go closer than the shell, and I go inside the shell, well, then the shell will no longer attract me. Right?
Right.
So it's really not part
If
of
it's
the
evenly
black hole.
distributed, yes.
Yeah. Anyway, in astrophysical reality, might as well just point out, how do these things happen? Like, for example, one way is in a supernova explosion. So a massive star, runs out of nuclear fuel, can't hold itself up anymore, collapses, and then there's a giant shock and part of its material is blown away, but still there's enough inside to collapse and form a black hole. That's one way. Another way is actually, we just saw, I guess it was about 2 years ago now, when the two neutron stars coalesced and the gravitational wave signal was seen by LIGO. Well, now, one neutron star is barely not a black hole. It has so much mass, condensed so much, it's almost enough to be critical, beyond critical, and become a black hole, but not quite. But when you put two of those together, it becomes too much to hold up. And so after that collision and some material is thrown out, what's left behind is almost certainly a black hole.
With regard to a statement you made a few moments ago, consider an element of mass inside and an element of mass outside. Are the forces equal and opposite?
Forces. So the concept of force is not really how general relativity
Go to energy, I guess.
works things out. Yeah, I mean,
Here's some water for you if you want
thanks.
that.
Okay, let's see.
The concept of 3 kilometers is a little bit hard for people to imagine. I ask my students to calculate the Schwarzschild radius for the Earth, and it comes out to 0.9 millimeters. Then they really understand how dense things are.
Yeah. Well, a neutron star radius is about 10 or 12 kilometers, so it's only 3 or 4 times a black hole radius. But then again, a neutron star is also hard to imagine. One giant nucleus. Anyway, okay. Let's see. I think, one reason I think people had so much difficulty understanding this is they didn't really have a picture of it. I showed you the picture of the spillway with the dam and the water going in. That's nice, but I don't even think people had that analogy. In general, I think people didn't understand this well until there were pictures of it, and I want to show you. I'm going to skip one of these, but show you this picture by Roger Penrose in space-time that I think makes it completely clear what is a black hole and what's going on with a black hole. So this is one of these pictures of space-time, and time is going up along this arrow, so up on the diagram like before, and here's collapsing matter, just like before I had the tube of the Earth, but now it's getting smaller in cross-section because it's collapsing. So this could be that Oppenheimer-Snyder collapse situation. And what's happening to the gravitational field is that the light, so Penrose draws these light cones. So what is a light cone? If we pick any point in space-time, like that one, and shoot off light in all directions, it expands like a sphere, just like the pebble in the water expanded like a circular ripple. And if you look at all the points that the light would reach on expanding on that expanding sphere, it forms a cone at that point, pointing this way, which is future in time. You also have in the past the cone of light that could have reached that point. And this is called the light cone. And it indicates something very important about the metrical structure of space-time. And what Penrose draws is what's happening to the space-time is this. The light cones are tipping over because light is being dragged in by the gravitational field. And in fact, like here's a picture of a photon trying to escape. It's not going in a straight line because the gravitational field here is pulling it in. And if it actually starts too close, it never gets anywhere. It just runs right up along the edge there, and that's the event horizon. So what's happening at the horizon here is that the light cones are completely tipped sideways, so their outermost edge coincides with the surface. And this is exactly the same as what I showed you before with the circle of the ripple of surface waves that was just tangent to that red line on the spillway. That's what's happening. If you go inside there, if you're curious to find out what happens, well, you pay a big price because you can never escape. In fact, you'll hit this infinite curvature region in a finite amount of time. It's called a singularity. This is a true singularity, unlike Schwarzschild's coordinate singularity.
Would you repeat that?
Yeah. If you fall in, then you live at most a finite time here, and that's a very short time. It's about the time it takes light to cross 3 kilometers if this is a solar mass. So that's like microsecond or 10 microseconds. Yeah. And you will hit a place where gravity becomes infinitely strong. And in general relativity, that means the curvature of space-time becomes infinite. You'll be shredded because you'll be stretched in one direction and squeezed in the other two directions. What? Spaghettified. And the thing is that's really fascinating, we do not know what happens like at that point. That's a breakdown in the theory, and it's just the end of our story as far as known physics goes. General relativity is quite well confirmed in many ways, but we really can't say once you get close to that singularity, we don't know, something has to change because that theory can't describe. You know, it's when a classic example in physics where some quantities become infinite in your theory, which means that your theory is wrong and you don't know, you're missing some physics.
So the event horizon is not the singularity.
That is not. In fact, you could fall across there and notice nothing. In fact, for a supermassive black hole, like one in the center of a galaxy could be 10 billion solar masses worth of mass. At that point, the radius of that, instead of 3 kilometers, is 10 billion times 3 kilometers. That's a huge horizon, and if you fell across it, you wouldn't know that you fell across it. There wouldn't be any noticeable thing. But you would still get to a singularity in the middle.
Or it could be 13.76 billion years, light years.
The whole universe?
Yeah.
No.
I don't know how to make that one, but
The event horizon of the whole universe is the event horizon.
it's a
of the black
different
hole.
kind of horizon, yeah. As far as I know, it
I'd like to
doesn't
know
have
the difference.
It doesn't have that singularity inside it. Beyond that horizon, you just keep expanding, and there's lots more space.
Maybe you lose the dimension of time when you reach that.
Right.
place.
Yeah, something like that. I mean, it has to be something really radical. Maybe you have a bounce into another branch of the universe. Maybe time just stops flowing, like you said. And you could try to scratch your head and see how could that ever happen. It's one of these things where we have to just speculate. We don't have any basis. So there are theories, but no knowledge of that. Yeah.
Hawking talks about time becoming imaginary.
Mm-hmm.
You know. So the c squared t squared term changes sign.
Right.
And in that case, your forward dimension becomes.
Yeah, in fact, this brings up something fascinating that Hawking was interested in cosmology when he was talking about that and how the universe could have emerged from like a time before time, like before there was time.
And no boundary.
No boundary. It was Euclidean. It was purely spatial, and then time sort of came into being, even though that's not the right way to say it, because came into being already assumes it's happening in time.
Yeah.
It's really amazing that Lemaitre, who I mentioned earlier, also had already speculated about that if you go backwards in time in cosmology, you get to conditions that transcend known physics. and that the very existence of space and time could be contingent on something that happened there, and before that there was no time. He even speculated that. So it's quite natural idea what you mentioned, that maybe if that's possible in the past, then why not in the future? It could be you run into some place where time stops.
Is there a problem that we don't have the language to think about these things?
Possibly, although we have math and we can make up mathematical models. What we don't have is observations. It's a very frustrating thing because, you know, when Einstein invented general relativity, there were just a very small number of possible observations that could test this beautiful abstract theory. Now we have many, many concrete observations. It's even a tool in astronomy, etc. He thought nobody would ever see gravitational waves. We've seen them. But this is different because this is saying unless physics violates the principle that nothing can go faster than the speed of light, nothing will ever, you will never see anything inside a black hole unless you're willing to sacrifice your life and fall in to look at it.
And then you can't tell anybody about it.
Then, right.
Yeah.
So go in together with somebody holding hands. Let's share the knowledge.
The speed of light is 0 at the event horizon, then you can't fall in.
That's actually not true. You can definitely fall in. That's the point about the proper time here being, so the speed of light is always c, as measured by a freely falling observer.
It is always exactly 1 light second per second.
Yes.
Tautologically.
Yeah.
The problem
In fact,
with-
it is today defined that way.
The problem with
Yeah.
C is that C is not fixed because time can contract or expand. So that it's not a fixed quantity ever.
1 light second per second is fixed.
Yeah.
And meaningless.
And meaningless, yes.
Maybe we should continue.
Yeah.
I'm talking
okay.
about in the physical world,
So,
it doesn't mean it.
just in a word, the way in general relativity, the right way to think about the speed of light is this light cone structure in space-time. So if you just picture space-time, what the line element of general relativity tells you is where's light propagating? And it's on a conical shaped surface like that. And that is really what it means to talk about the speed of light in general relativity. But to assign it a number, I would say isn't meaningful. That's an arbitrary units thing.
The visible universe is basically what's in the lower cone?
The visible universe to a person at the vertex, yes.
Yes.
Everything on and inside.
I
the
did a
loop.
calculation once, if you have a cone like that inside a sphere, then the past is almost exactly 1/11 of the total. Which
Can you tell me about that after this?
Yeah, let's continue.
Okay, so
There's a lot of good stuff to get to.
Yeah, so let's look at what's happening now. There's a key, even though we can't see the singularity inside of it, there is a very conspicuous consequence of this bizarre nature of a black hole. And you can see it, I think, from this, looking at these red arrows and thinking about them. So this is a question of what is the symmetry of the space-time under time translation. The time translation symmetry describes a static object. And if the black hole is just sitting there, it sure looks static to us from the outside, right? Nothing's happening, the star collapsed, it's sitting there for 10 million years, nothing's happening. And that corresponds to translating along a red arrow outside towards the future. Nothing changes as you slide along that direction. But by the same token, in general relativity, nothing changes when you slide along that direction inside the horizon either, or on the horizon. But look closely at that. Along the horizon, you see that that red direction is tangent to this light cone. So that red arrow is actually moving at the speed of light. So the time translation symmetry out here becomes a speed of light translation symmetry, and then inside the black hole, the arrow is actually pointing outside of the cone, so it's in a space-like direction. It actually becomes a spatial translation symmetry inside, and while it's a time translation symmetry outside, but taken together, it is asymmetry. This could only happen in general relativity, that a symmetry could be globally a symmetry of the situation, but it's a time translation symmetry in part of space-time and a space translation symmetry in another part of space-time. Actually, it's not only in general relativity. I'll show you later another way. But so the consequence of that is that the conserved, you may know that conserved quantities in physics are related to symmetry. So time translation symmetry accounts for energy conservation, space translation symmetry for momentum conservation, rotational symmetry for angular momentum conservation. And so this time translation symmetry is associated with some kind of an energy out here, but here it becomes space translation, so it's a momentum. That makes a big difference because while energy is bounded below, you can't have negative energies, because if the world supported negative energy states, there wouldn't be a ground state of the world and everything would be unstable. So it's a fundamental principle of the vacuum that there are no negative energy states. But there are negative momentum states. There's no problem having negative momentum. So therefore, this conserved quantity can be negative inside the horizon while it's only positive outside. Well, okay, but that's inside the horizon, so who cares? Well, who cares is Roy Kerr, who figured out the rotating black hole solution in general relativity. In 1963, he found that solution, and it turns out that this time translation symmetry becomes space-like, not just inside the event horizon, but outside of it in a region called the ergosphere. So his work revealed that outside of a black hole, the time translation symmetry becomes space translation. And the reason is that the black hole spinning is like dragging space around with it, like a whirlpool. And the space is sort of moving faster than the speed of light relative to the outside. So you couldn't, if you tried to sit there without rotating, you would have to go backwards faster than the speed of light. In other words, the dragging of inertia forces everything to co-rotate. So if you don't rotate, you're going faster than the speed of light. And therefore, the symmetry is space-like. And therefore, energy can be extracted from a rotating black hole, which was first realized by Roger Penrose in 1969. It's called the Penrose process. And he realized that by lowering, so here's the thought experiment that he did. Here's a picture at sort of one time slice of a black hole that's spinning. And let's see, the absolute event horizon is this circle. And outside of it is the boundary of that region where negative energy states exist, called the stationary limit. And what he's showing here is that these guys on this scaffolding can lower a body on a long rope into this region, into a negative energy state. And by energy conservation, that means that they're getting positive energy here. So they're getting energy for nothing? Well, not really, because they're going to drop that negative energy object into the black hole, and therefore it's going to absorb negative energy and lose energy. Which means what's really happening is they're extracting rotational energy from this spinning black hole. And a spectacular instance of that is probably some of these astrophysical jets that are observed by radio telescopes, and maybe X-ray also. So somehow spinning black holes with a plasma around them manage to shoot out hyper-relativistic jets of matter. And it's believed through this something called the Blandford-Znayak mechanism that basically the plasma is tapping into the rotational energy of the black hole by a mechanism quite similar to this. It's actually a Penrose process. Okay, so you can extract rotational energy from a black hole.
When that happens, does the Schwarzschild radius decrease?
Ah, that's exactly what I was about to address. So that's fascinating. Who asked me that question? Thank you. Yeah, this is exactly the essential point.
Michael
So
Hyman.
certainly the mass decreases
Hyman.
because E equals mc squared. So the energy is determined by the mass. And you're extracting energy, so the mass is decreasing. So you might think that therefore the size of the black hole would decrease. But you're also extracting angular momentum when you extract energy. And the size of a black hole depends not just on the mass, but also on the angular momentum. So it turns out, what Penrose realized is when you extract energy, even though that the black hole loses mass, it never loses area. The area of its event horizon could never decrease. That was later formally proved by Hawking and was called the area theorem. So you're extracting energy, but the area is not decreasing. Now, you might think, what's the most efficient way I can extract the energy from the black hole? And somebody analyzed this shortly after this, named Christodoulou at Princeton. And he found that the most efficient way, he didn't put it this way, but let's put it this way. The most efficient way is if you don't change the area at all. If you do change the area, you've wasted some of the energy you could have extracted. So the most efficient energy extraction is with zero increase of area, and otherwise area always increases and the area can never decrease. And what does that remind you of?
Entropy.
Entropy, right? A process which doesn't increase entropy is the most efficient process, let's say, that an engine could operate at. The Carnot efficiency is determined by just saturating the inequality that you don't increase entropy. So people immediately thought, hey, that's weird. A black hole has this quantity that's behaving like an entropy, it's the area. Could area be entropy? And that's the question that Bekenstein asked, because really Bekenstein was a graduate student in Princeton in 1968 or so when he was doing this. No, it couldn't have been that, 69. So it's early 70s, 71. Wheeler asked Bekenstein, what if I have one of these spinning black holes and I drop a teacup into the black hole, and the teacup has got some entropy because it's some thermal state of liquid, and I drop it in, the entropy of the outside world decreases because all that entropy disappeared and nobody will ever see it again because it's inside the black hole. Nothing can escape. And that really bothered Bekenstein and it bothered Wheeler because it seemed like a violation of the second law of thermodynamics. Unless you're willing to dive into the black hole with the teacup and say, no, the entropy's still there. But that's, for the outside world, thermodynamics is violated. So Bekenstein thought about it. Here's a picture of him at the time. I couldn't get a non-fuzzy one. And he said, well, wait a minute. Actually, if I drop that teacup into the black hole, something is going to happen. I'll be adding mass to the black hole, and the black hole will get bigger. And so maybe I should assign some entropy to the black hole and say that the black hole's entropy compensated the loss of entropy in the teacup. And so here's what he proposed. That's when he said, let me suppose that black hole entropy goes like the horizon area. Since I know that the area can't decrease, that's a good candidate for it. He had to measure it in some units of length squared, so partly by dimensional analysis, he assumed Planck length squared. If you do that, you come up with an enormous entropy. 10 to the minus 33 centimeters is the Planck length. That is, orders and orders and orders of magnitude shorter than anything we've ever probed in an experiment. So it's some humongous entropy. And he proposed the generalized second law that, okay, the outside entropy may decrease, but if you add that to this black hole entropy, then that sum will not decrease. And his reasons for proposing that, first, like I said, the area never decreases. It's an extensive property of the black hole. Entropy should be extensive for a system. And also, he actually did a quite sophisticated analysis using general relativity and the Heisenberg uncertainty relation to infer that the minimum area increase was exactly what was of order of the Planck length squared, independent of the black hole's mass, spin, and charge. So, in other words, if you think about entropy as a measure of missing information, and you quantize that information in bits, the the minimum unit of entropy increase of a system would be log 2. That's one bit of information. He was thinking about it that way and saying, well, if the minimum area I can increase the black hole by is the Planck length squared, that's taking the uncertainty relation into account and general relativity, then I guess 1 Planck length squared should be the unit of entropy of a black hole. And so that's how he came up also with this coefficient. He didn't know this numerical prefactor precisely, so he just, it could have been some number of order unity.
Isn't it kind of silly to talk about entropy outside as being independent of the entropy inside? Because we always thought that entropy was for the whole system. And just because you can't see into the black hole doesn't mean that it doesn't contribute to the entropy.
You could try to take that viewpoint, but it would render thermodynamics useless for the outside observers, because you're never going to see what's inside there. So if that were the only way to deal with it, what it would mean is that for practical purposes, if you're doing thermodynamics around a black hole, you can't use the second law of thermodynamics for your set of observables.
That's right.
Right, so I think that and it could have been that way. Turns out it's not that way. And it's a very deep thing that we're still trying to appreciate why, which we're going to get to here in the talk. But I guess one thing I just would emphasize about entropy is that it is an elusive concept. It's important to, if you think of entropy as missing information, you have to specify information about what. So entropy should always be defined relative to some class of observables that you have delineated in your system. In this case, the class of observables is everything that observers that stay outside the black hole can see. And I have to say, if I were alive at the time, let's say I was a graduate student. In fact, this is an interesting story, I'll tell you this. So Bob Wald, who's another major person in this field, who works more on the mathematical side, was a fellow student of Bekenstein's. And he just recently wrote an article reporting that he remembers that when he heard Bekenstein talking about his project in a group meeting with Wheeler and the other graduate students, and they walked out of the room at the end of the meeting, Bob Wald said to himself, gee, I am so glad I have a good project to work on and not this crazy idea. And I have to say, if I were there, I think I would have thought exactly what you're saying. Like, okay, so thermodynamics breaks down at a black hole. Black holes are weird. Why not? But it's not that way. It doesn't work that way.
Well, I didn't say that they break down.
Well,
thermodynamics. It's just that we living outside the black hole cannot see the whole system.
Yeah, but think about the implications of that. Think of how you use the second law to come up with things like the Carnot efficiency limit of heat engines. Suppose I'm operating my heat engines outside the black hole and I allow myself to use the black hole as a sink to dump my entropy into. Well, then I can come up with a perpetual motion machine or something. It's outside, because I'm just operating outside. So I think like it really would be alarming and probably have consequences that seem unacceptable once you think about it. If we really could violate the second law for observables outside the black hole. Well, let's keep going, because you'll see it's just shocking and amazing that it turns out this really seems to be correct to assign the entropy to the black hole. And we'll ask, what does it mean? Why should a black hole have entropy?
Please go forward, I'm so excited.
There's a definite answer to that. Yeah.
Give him a chance.
If the outside world loses entropy, does it gain anti-entropy?
By definition, yes.
I mean, I know the word trope because I know music, so that's finding something, so.
Yeah, I would just say, by definition, you could call losing a positive thing gaining its negative.
So it's,
Oh.
all right. you
Much
lose
easier to
it,
say the
Let's talk
entropy
about it later.
decreases.
Fine.
I don't think it's a helpful way to formulate it, though. Okay, let's see. So Bekenstein realized that if he was going to assign an entropy to the black hole, that means it should have a temperature, which in thermodynamics is defined as the derivative of entropy with respect to energy. The reciprocal of that is temperature. And the black hole has an entropy, the black hole has an energy, that's its mass. So it should have a temperature, and if you work it out according to his formula, you get something that's proportional to h bar. So it has a temperature proportional to h bar, quantum mechanical temperature, and it's h bar times something that's called the surface gravity of the black hole. It's kind of a measure of how strongly accelerated things are near the black hole. So, but the validity of his generalized second law requires, this is not just a mathematical formula, that it's actually a real temperature. And the reason is, if you put the black hole inside a thermal bath of radiation, and it's absorbing radiation but not emitting any, then if its temperature is hotter than the outside temperature, then the net entropy will decrease, because heat's supposed to flow from a hotter reservoir to a colder one. And here it would be flowing from colder outside the black hole to hotter inside the black hole. So this is just a thought experiment, but it revealed that his proposal, let me go back to this, I don't want to lose you on this crucial point. He proposed that we generalize the second law to include a term corresponding to the black hole entropy, and that would never decrease. But if this is going to be true, you can infer it must be true that the black hole has a real physical temperature, although Bekenstein didn't realize this. He didn't realize it. He could have, and it would have been, it's already an amazing piece of work he did, but if he had realized this and said, I'll stake my reputation on this, but somehow or other a black hole really has a temperature, and the reason you never noticed is that it's proportional to h bar. Well, it turned out he didn't do that, but somebody else did discover it, and that was Hawking. Stephen Hawking's black hole radiation. Just the next year, Hawking discovered that if you think about quantum fields, if you think about the fact that a black hole is immersed not in empty space with nothingness, but it's immersed in empty space with the vacuum fluctuations of all the quantum fields, that those quantum fields would be what would give the black hole a real physical temperature, and the black hole would radiate, and he calculated the temperature it would radiate at, and lo and behold, it was, oh, I didn't write it down, it was the temperature that Bekenstein had inferred, but with a very specific, precise coefficient, because Hawking was able to calculate this just using standard quantum field theory in a black hole spacetime. So, Hawking had actually previously been a total skeptic about Bekenstein's idea of attributing real entropy to a black hole. He had almost, I would say, ridiculed it, certainly rejected it. And he and everybody else who were leaders in the field had rejected, they thought Bekenstein was just taking too seriously just a mathematical analogy. And yet Hawking found that actually the black hole has this temperature. So what is happening in Hawking radiation, and this will lead us back to what's happening with the entropy. Where's the entropy really coming from? So remember, I mentioned that the time translation symmetry is space-like inside, and therefore there's negative energy states accessible, and that implies that the quantum vacuum is unstable. So what happens to the vacuum when you have a black hole is it peels apart. Vacuum is full of, let me pause to say this, because this is a concept that might not be clear to everybody. So vacuum you think of as nothingness, right? Just take everything out, suck all the air out of your room, all the molecules, there's nothing left. It's nothingness by definition, right? Okay, wrong.
Wrong. That's the philosopher.
Because let's consider, for example, the electromagnetic field that carries the light that's lighting this up. That field is a quantum mechanical system, and each mode of the field is like a harmonic oscillator. And like a harmonic oscillator in quantum mechanics cannot be sitting exactly at zero without any motion, because that would violate the Heisenberg uncertainty principle. There's a 0-point motion of any oscillator. Similarly, there's a 0-point motion of any mode of the electromagnetic field. So when we say the vacuum, all we really mean is that the field is in its ground state. It's not that there's no field, it's that it's in its ground state. And when we have a photon, that means it's in an excited state. So vacuum is not nothingness, it's a whole lot of somethingness. And what happens is the vacuum is unstable here, and it kind of peels apart, and a vacuum fluctuation outside can escape and become a real photon, let's say. Let's say we're talking about the electromagnetic vacuum. And when that happens, it's got a pair. It happens as a kind of pair creation process. In fact, the way I think about it is it's gravity, it's tidal force. Let's say here's the surface of the black hole, and this is the inside. Let's say I have a vacuum fluctuation pair, and this one is trying to climb away, and this one is also trying to climb away, but this one is outside the horizon, and this one is inside. Well, this one's outside, so it's the lucky one. It barely manages to escape. This one's just inside, so it's unlucky, and it gets dragged in like that, and they get separated. Whereas if they'd been in flat space, they would have just, without gravity, they would have just happily propagated together with each other and never separated. So it's a tidal effect of gravity sort of peeling apart the vacuum, and it gives you this temperature that's, like I said, proportional to h bar. By the way, it's interesting, what's the number?
Yeah.
If you take a black hole with the mass of the sun, and you put the numbers in, you get 62 nanokelvin. So it's a very low temperature for an astrophysical size large black hole.
Oh, okay.
But it's possible that there are black holes that formed in the early universe, much smaller than stars, just because of chaotic, inhomogeneous matter conditions. And if that happened, they could have been evaporating radiation for the age of the universe and shrunk in size. And the smaller the black hole is, the larger the surface gravity is. It's inversely proportional to the mass. So once this could become extremely high temperature, and it could even emit, gamma rays, and people look for the signs of those gamma rays. Okay, so let me figure out where I am.
One
in
thing
time.
about this equation is we're used to thinking about nanokelvins these days.
Yes.
And so 62 is something that is almost measurable.
It is measurable. I have been working on, so there's a guy who did an experiment in Israel using a Bose-Einstein condensate in a trap in which he swept a kind of step in the potential through a kind of a cigar-shaped condensate. And that set up a flow in the condensate, and the condensate flow was faster than the speed of sound in that condensate, creating thus an analogy to a black hole event horizon, similar to the one I showed you earlier with the surface waves. And that horizon has a Hawking temperature that's just around the same as this, nanokelvin, 60 nanokelvin, which is a temperature that people can actually measure in Bose-Einstein condensates. They can cool them to that temperature and measure it. So he actually observed Hawking, the analog of Hawking radiation in this Bose-Einstein condensate. But that's another story for another time.
Yeah, you'll have to go back and tell us that one too.
I guess I'm not gonna have, what I'd like to make, so I'm really running out of time.
Well, don't worry.
The key part that I have to tell you without ending, before I end, is what does this Hawking radiation have to do with the entropy? How does it explain potentially the origin of the entropy? And why a black hole has entropy? And I can explain it, I think I'll explain it not mathematically, but just by going back to this picture. Hold on, which picture do I want to show? Go back to this picture. So the vacuum fluctuations actually, remember we're talking about quantum mechanics, they're entangled with each other. And so if you're only observing things outside the black hole, you actually observe a mixed quantum state. I'm going to go to this right here. So hopefully this one example of a quantum entangled system is familiar to you. This is called a spin singlet. So it's 2 spin 1/2 degrees of freedom. Think of it as 2 particles with spin. This represents spin up in the z direction and spin down. And the first particle is up, the second one is down, and then you make a quantum mechanical superposition of the minus sign of spin down and spin up. And that's called a spin singlet. It's a rotationally invariant state, and it's quantum mechanically entangled. What that means is that it means that each spin by itself doesn't have a definite state. If you only observe the first spin, there's a 50% chance it'll be up and a 50% chance it'll be down. And it's completely random which one it is. But taken together, the whole thing is in a pure quantum state. If you only observe half of it, therefore there's entropy. In fact, there's 1 bit of entropy exactly, because probability of 1/2 for up, 1/2 for down, and Boltzmann's formula for entropy, given probability, would give you log 2 in that case. So this origin of entropy is something that actually Landau realized early on in the history of quantum mechanics. If you take a quantum composite system and restrict attention to a subsystem, even if the whole is in a pure quantum state, the subsystem will have entropy and be in a mixed quantum state. So with a black hole, we have a subsystem. If we stay outside of the black hole horizon, we're looking at a subsystem of the whole thing. Of what whole thing? Well, of the vacuum. The vacuum is a quantum mechanical system, and by virtue of being outside the black hole, we're only accessing a subsystem of it. Okay, so then for every kind of pair like this of quanta in the vacuum, we get 1 bit of entropy. Well, that's an awful lot of bits. Why? Because if you take the electromagnetic field and decompose it into modes, every wavelength is allowed in every direction, down to a very, very small scale, maybe where we stop understanding it at the Planck scale. So it's an incredible density of entropy just because we're outside of the horizon of a black hole. So that's the proposal that Raphael Sorkin first made, that we can even estimate it and find out it goes like the area. So this is getting into something technical that's probably only familiar to some, that you could form what's called a reduced density matrix, the probabilistic description of a subsystem in quantum mechanics, calculate its entropy, and it comes out proportional to the area of the surface if we're talking about a subsystem of the vacuum. In fact, it comes out infinite because there are an infinite number of degrees of freedom in the field, ideally. Physically, really, it should be finite because of some physics we're leaving out. But
So you have some cutoff?
You have to put it in by hand here, and once you do, you get the area divided by that cutoff length squared. If we assume, as is natural, that the cutoff length should be the Planck length, then this coincides with Bekenstein's formula for entropy.
Yeah.
So it seems like the right track we're on is that actually, yes, a black hole really does have entropy because we're really looking at a subsystem of the universe of the vacuum. If we hadn't taken the Hawking radiation into account, we wouldn't have noticed it. But it's there. It's proportional to h bar, and it's there, and the entropy is proportional to 1 over h bar, and is huge. Okay, so I have to figure out how to wrap this up without.
Well, this is wonderful. Take your
Let me
time
see.
and don't
No,
rush the end.
We're in no hurry.
We got all day.
We got all day.
Yeah, we got all day.
He's retired.
Yeah, okay, but there's limited patience and limited ability to absorb
so
things. So, let me just think about what I
Sorry.
should say to wrap it up. I think I'll tell you one more story that relates this to the Einstein equation, and because that'd be another nice piece of insight, and I'll just leave it at that. There's a whole bunch. I just want to suffice to say, we've just touched the tip of the iceberg. This was discovered a few decades ago, and there's an eruption of activity lately
It's a
because
volcano,
new
not
connections
an
have been
iceberg.
pardon?
It's a volcano, not an iceberg.
It turns out to be, which is very thrilling, right now, because of developments in string theory and general relativity, quantum field theory, it really seems like this idea that the entanglement entropy, it's called, of the vacuum, is related to geometry in a crucial way. So the fact that the entropy is proportional to the area can be read in the opposite direction. The area is proportional to the entropy. In other words, we can start asking ourselves, well, wait a minute, what is the origin of geometry in space in the first place anyway? If all of space is full of the vacuum, and the vacuum entanglement measures the area, well then maybe that's what area is. Maybe geometrical area should be, we should look for the origin of geometrical structure of space-time in the quantum entanglement of its degrees of freedom. And there's a lot of evidence for that, which I can't go into much of, but I just want to tell you one bit of that story. I'm going to jump to this. So consider, is this where I was going to start? No, I was going to start here. Let me first tell you a way of thinking about what Einstein's equation is. This is an amazing thing that you can explain it this way. Consider any point in space-time and shoot out straight lines from it at one instant of time and make a ball and measure the volume of that ball and the surface area of that ball. Well, if the ball were in flat space-time, there's a standard relationship. The surface area is 4 pi r squared, the volume is 4/3 pi r cubed. There's a fixed relation. That relation still holds when space-time is curved according to Einstein's equation. Any small ball, has to be small compared to the radius of curvature, of a given volume has the same area as it would have had in flat space-time. This is the empty space Einstein equation. And you don't need tensors, 10 differential equations of partial differential equations of 4 variables, nonlinear, all that stuff. This summarizes what that equation says. It's quite amazing. If you do have matter, then the area is not the same. In fact, it's less. There's an area deficit. If you put matter inside the ball, the area shrinks for the same volume by an amount proportional to the energy that you put inside. Also proportional to the radius of the ball and Newton's constant. Okay, so that's just a way of thinking about Einstein's equation. Now I want to relate that to entanglement in a different way without a black hole, but just with entanglement entropy. So let's now imagine just a ball-shaped surface in space, like this one right here. No black hole. I could think about dividing space between the inside and the outside, and the vacuum would have entanglement entropy across there. And I could ask myself, is that entanglement the most I could possibly have for any state? Okay, I'm going to assume that the total entanglement entropy is the surface term, area. In fact, this is Bekenstein's formula for entropy, so I'm going to assign a Bekenstein entropy not to a black hole, but to this surface, which turns out is the correct thing to do. But I might also have entropy inside, right? I could just put some tea. I could have put a cup of tea inside that ball, and that would add some entropy. So let's try to do that. So here I'm going to take 2 qubits, like my spin singlet state, that are entangled with each other, and I'm going to place one of them inside. It looks like I could just increase the entropy inside this ball because I already have this area, right? That's my Bekenstein type entropy. And now I've added 1 bit log 2 of entropy by adding this entangled qubit. Does it work? The answer is no. Because according to quantum mechanics, if I really knew that I put this bit inside here, and if the size of this ball is L, if the diameter is L, then the uncertainty relation of quantum mechanics tells me that I must have given this thing an energy at least as big as h bar divided by L. This is a form of Heisenberg's uncertainty relation. But that means I added some energy to the ball, and now because of the Einstein equation I just showed you, that means that there's a deficit in area. The curvature that Einstein's equation tells us is tied to energy density, tells us that the area shrunk when I tried to increase the entanglement entropy by putting this bit in there. And how much did it shrink? Well, if I use the Einstein equation, I find it shrank just enough to foil my attempt to increase the total entropy of the ball. The marginal case is the entanglement stays the same, the total entropy. So it's almost as if the Einstein equation, what it's telling us about space-time is that the structure of space and time is such that the entanglement in a region is maximized, and entropy is maximized. Well, what does maximizing entropy normally mean to us? It means equilibrium, right? You spread all your energy into all the degrees of freedom out as much as you can and maximize entropy. So somehow this suggests a picture of the vacuum of space is a kind of thermal state where the entropy of entanglement of all the quantum degrees of freedom is just spread out and maximized. And any deviation that inhomogeneities try to make, well, to first order won't change the entropy, just like they won't for a gas in thermal equilibrium, because it's at its maximum, the entropy, at fixed volume. So this is, again, tip of a volcano, I guess, where the volcano is melting the iceberg and we're flowing down with it. I'm not in a canoe. Oh, wait a minute, better get not carried away. I can't
go. Don't go to Hawaii.
I'd have to give you a second talk on where this is leading to us to today, but you can maybe tune into things like Scientific American articles or various places to see online stories about it. But it's really an area of quite a bit of excitement because of the development in string theory that led to what's called the holographic principle. But I think I better just stop because, yeah, it's enough, it's enough for one talk.
We better thank you.
This is a wonderful talk. I usually go to NASA after this.
Really great.
Traffic was no bad right here, and then it's good.
Shores,
to the whole
Shores?
hospital, and then it's bad again.
Shores algorithm?
Regarding calculations with qubits.
I don't know what lemma you're referring to.
This is the lemma that says that if you have to do error correction because the entangled pairs are subject to influences from the outside, which would totally be rid of.
Yes.
You better make the calculation in a hurry.
Yes.
And as I understand, I don't claim to understand, because that's the reason I ask you. He comes up with a result of what tolerance there is for such errors.
Yeah.
Can you still correct it at all?
My name
Huh.
By the way, there was an error, there's a letter written to the Washington Post by the president of my ex-university, University of Southern California, which is totally wrong. He confuses entanglement with influence.
Oh, yeah. That really bugs me.
It's something that propagates.
Right.
And propagation of influences occurs at sea, and it's not at
That
simultaneous.
confusion is propagated all the time by journalists and even by physicists. I totally agree with you. It's really interesting that you mentioned quantum error correction, because one of the developments that's happening now is actually a realization that, in a sense, space-time might be analogous to a quantum error correcting code.
Do you know of anyone at the university?
I can give you a reference to like a website blog by some people at Caltech that tried to explain that in a rough way to without needing to know details, just introducing the idea.
It sounds like an awfully delicate subject to me.
It's very it sounds really out there, but it's there are a lot of remarkable things happening with it. So I think I don't think it's crackpot at all. It's and it's actually
anyone
quite.
At the university you know who's working on these things, calculation with qubits, possibly with Schwarzschild?
Well, we have a whole quantum computing group at Maryland.
Chris Monroe?
Yeah, he does the experiments on it,
isn't it?
and there's the Quicks Institute.
Yeah.
So if you want to chat about details about things like that, you should just go over there one day and find somebody to talk to.
Question, you mentioned also that string theory is starting to come into this. There's also this quantum loop theory. Where are we in terms of this string theory versus quantum loop versus, I guess, the generativity people?
Yeah.
I guess, are they finding connections, or is one more connected with the other than the other?
So
I'm
far
just
there's
curious.
no, yeah, it's a good question.
Because I was at that talk a couple weeks ago at the where he talked, where in one space you see entanglement, and in the other space you start to see the Einstein's equations.
Oh, yeah, you were at the colloquium by Mark Van Ramsdorff.
Yes, the colloquium. So I'm just wondering, roughly where are people?
That's based on this holographic duality between a conformal field theory, he called it the gravity ball or something,
Okay.
and space-time inside. That emerged, that realization came out of string theory. It stands on its own as an aspect of quantum gravity,
Okay.
but it was first realized by working within string theory. Didn't come out of loop quantum gravity.
Oh, whatever.
In my personal opinion is string theory has made a lot more headway than loop quantum gravity. That's more like true headway.
Okay.
And nobody's yet realized how they are related, how those two subjects are related to each other. They might be in the end, but they take very different starting points for how to try to understand quantum gravity.
Okay.
I can tell you about afterwards how they're different, but they're different, and I think because of the starting point the loops take, they're aiming higher at the beginning and then not getting as far. That would be in one sense the way I.
Because last I heard about string theory, they came up with something like 10 to the 900 or whether possible
Different
universes,
vacuum.
and then I thought they kind of gave up on it. So I'm
No,
not
they
sure
didn't
where
really
we
give
are.
up. Now they just accept that as an unfortunate consequence of the
Well,
theory.
those are possible universes.
It's
That
not-
doesn't mean they all
It
exist.
doesn't contradict observations. It just makes it hard to predict
Well,
things.
they've also assumed that there were an infinite number of possible universes, and that doesn't make sense.
Yeah, well, that's what I'm saying.
Yeah, I would say, well, I'm going to more than one conference this summer on this topic, and I'm not even going to all of them. And there's a school at Princeton for training new students in this area this summer. There's really a lot of activity.
Okay.
And it's,
Okay.
Harold here and Jack and I have had a course in Clifford algebra.
Oh.
From a mathematician who's sort of one of our immediate friends.
Yeah.
And,
Okay.
Great minds think alike.
Harold has emphasized.
What does that have to do with
pixelation.
me? For us?
Yes, yes.
Planck's length, Planck's
Okay.
time.
Yeah, I
and
think
all
it's
these
waiting
things
for me.
Okay.
Involve pixelation of space.
It means that great
Oh, he
minds
left his.
think the same as both of you.
And, no, I'm not going that far. Let's see, Alan Gromborski taught us how to deal with higher dimensional spaces, and if you have what's called a manifold.
Yeah.
And it's embedded in a larger manifold. That, what do you call these objects you go around a circle, you don't come back to
That's
where
the
you
loop.
wound up.
That's the quantum loop.
Oh, right, yes. I think that's a visualization of what gravity does. It takes time for something to get around the loop, and in that time, if you have the distortion of space associated with masses,
Yeah.
and then some distance, distance mismatch, and that's how far the system has traveled in space.
But that's torsion, that's torsion.
It's called hysteresis.
Yeah, but is that, what you're talking about is torsion.
Right, if you go around the loop and come back, if you carry a vector around the loop and it comes back rotated, that's
It comes
curvature.
back out of joint.
If it comes back out of joint, that's torsion.
That's
yeah.
torsion. Of course, Einstein set that to zero in his initial thing, because he wanted to be able to derive his Christoffel symbols in terms of
Yeah.
the metric tensors. So
Standard
he
formula.
immediately assumes that it's zero.
Which it is in the standard formulation of,
Right. And if there is any torsion, you can also show that any results
Have an napkin, yeah.
is smaller by many factors of
we
more
did- we
g's and
didn't
c
need that.
squares. So it's not apparent that
Did he
you
get you
ever
wet?
have anything
Little bit. That's okay.
terribly
Thank you.
observable
You're so
in an
understanding.
experimental situation. Of course, weight, you never know. Because, people originally thought that 62 nanokelvins was infinitely cold, but now we're
No,
sure
it's not.
it didn't.
Not at all.
yeah, isn't that amazing?
Yeah.
My
Yeah, it
battery
really is.
died.
It was a wonderful talk.
This was a wonderful talk.
Great.
Thank you very much.
Well, you're very,
I
very
would like a
welcome.
copy of your slides to
Really
post
great.
on our website.
Okay.
You can either email it to me or
I'll email because I want to clean something up before I send it to you.
Okay.
Are there any
I will
factors
send it to you
that
and-
are
Send
missing
me
in
a
that
request just to
equation?
make sure I don't forget.
Okay.
Pardon?
You got A over 4 pi g, are there any C's missing there?
Yes, I set C to
Okay.
1 there.
Okay.
C to be 1.
I thought so.
It's,
Okay, good, I'm happy.
Yeah, C
I'm
cubed.
happy.
Yeah, I did
Didn't
an analysis that showed if C is equal to 1, that's where the 1s come from, and the 1/2 come
At
from
least
in,
these aren't dead, so that's fine.
in the quantum mechanics. And if every particle has an equal and opposite reaction on any force confining it,
Excuse me, I wanna-
then you add those up over a whole system and you end up with MC squared.
No, that's hard to follow.
It says that gravity is a result of equal and opposite reaction of
Are you-
any field on
For this class?
on particles.